Hi everyone. Today we're going to be talking about equilibrium and Le Chatelier's principle. So we're going to think about systems that come to equilibrium and also how Le Chatelier's principle allows us to predict what the equilibrium will do when we disturb it. Okay, so as ever, let's start with an overview. Okay, so we're going to talk about these processes we call reversible reactions, those that can go forwards and backwards and reach this point of equilibrium. We're then going to discuss Le Chatelier's principle, especially how it will allow us to predict what a system will do if we change concentration, temperature, or pressure. And then lastly, we're also going to think about catalysts and the effect they have on an equilibrium. All right, let's begin. So firstly, we're going to think about reversible reactions, these processes that we see that can go forwards and backwards. Because often in chemistry, it's very easy for us to think that reactions start at reactants and move towards products and that's it. But the reality is that many reactions can go forwards and backwards. So if you consider this first example here, we have what we call forward and reverse processes. The way that we show that is that we use this double-headed arrow in the middle. So what we're representing is two separate elements, A and B, combining together to form AB, a compound. And so what we're saying here is that as we start off, we will have all A and B as separate elements. So we have a high level of reactants to start with. And we have zero products because the reaction hasn't started yet. But what we're saying is that over time, the amount of the reactants will decrease as we use it up to make AB. But in doing so, that means that more and more AB is forming. So its concentration, its amount, keeps going up and up. But eventually we see that these lines here start to flatten out, that we're not producing AB quite as quickly and we're not using up A and B quite as quickly as before. And then we get to this point at which the line becomes horizontal, that we are maintaining a stable amount of both reactants and products. And what we're seeing is that lines up with this graph above, where we're looking at the rate of the reaction. So that is how quickly is each process happening. We start out with the forward reaction being very fast, but it's slowing down gradually as time goes on. The reverse reaction starts off with zero rate because we don't have any products. But as we form more and more of the AB, then the reverse reaction can happen faster and faster, but eventually both of them reach a point at which they are happening at equal rates. So we get to a point at which the rates become equal. That is, we're forming AB as quickly as we are breaking it down, which then corresponds to this point we call equilibrium, where there's no change in amounts. So we see that when we get to this point, our rates are equal, and we seem to have no visible change in our quantity of reactants, our end products. Okay, so we say that this point is equilibrium. Now the reality is that at that point, we still have A and B, particles of A and B combining to form AB. We still have particles of AB breaking down to form A and B. But there just appears to be no change because those rates are equal, where they're swapping at equal rates. So so there is still change happening, but that we just can't notice it at the macroscopic level. And so the thing is that so that we reach this point at which equilibrium is established. But there was a man named Le Chatelier who was able to recognize that if you get a system that is at equilibrium, that system can be disturbed. That is, that point can be broken in some way. And what he noticed that will happen is that the system will adjust in such a way as to partially counteract that disturbance or the imposed change. So if we add something extra, it will adjust to try and remove it. If we remove something, it will adjust to try and add it, and so on. So you can see with the image here, so if we start with two systems, a system at equilibrium here, and we pour in water at one side, it will adjust until then they are both equal. And if we take water out from one side, then it will adjust again until they are equal again. Now, perhaps this diagram is a little bit of a poor choice in one respect because it's suggesting that we always end up with equal amounts, which is not true. But we establish an equilibrium point, and that's what we reach from one point to another. Okay, so what we're going to do now is we're going to think about how the system will shift once we've disturbed the equilibrium, and especially if we're only trying to partially counteract that disturbance. We're going to now focus on it in terms of concentration, pressure, and temperature. So if one of those three things is changed. So start off by thinking about concentration. So let's say we've got this system that has some yellow molecules and some green molecules in equilibrium with each other, just as a model. Okay, so if some yellow molecules are removed, then what we're seeing is that some of the green molecules, which they are in equilibrium with, will turn back into yellow to try and get back to this equilibrium point. Okay, so if we remove something, the shift will be to replace lost particles. Now, if we were to add more yellow, then it would shift the other way in order to remove added particles. So what we're seeing is that the equilibrium can shift either to the left or to the right only. That's all it can do. It's not a sophisticated control mechanism. It shifts one way or the other in order to counteract that change. Now, so if we removed 2 particles here, then it will shift, and perhaps we might only regain 1 extra particle. For argument's sake, we're partially counteracting that change. It won't re-establish to exactly the same level as before, but it will partially counteract it. Now, if we were to think about it in terms of temperature, what we're seeing is that when we're changing the temperature, we're adding or removing thermal energy from the system. So we're changing the motion of the particles in some way. So the equilibrium will shift to either favor the exothermic or endothermic reaction, depending on which way the temperature has changed. So if we increased the temperature, the equilibrium will shift in favor of the endothermic reaction because that removes thermal energy. If we decrease the temperature, it shifts to favor the exothermic reaction to replace thermal energy. So the principle here is exactly the same as it is with concentration if you think of energy as a term that we would write in our equation, like such and such plus energy. So if you consider it that way, then the behavior here is the same. We're shifting to replace something that was lost or remove something that was added. Now let's think about it in terms of pressure. So pressure, we're thinking about gas particles. So here we've got a system that's involving nitrogen, hydrogen, and ammonia gas. We'll look at that very shortly when we're thinking about the Haber process, which is what this reaction is about. So in this particular scenario, the pressure in this container is proportional to, that's what that symbol is, remember, proportional to the number of particles in that space. The more particles there are, the more collisions with the container, and the greater the pressure is. But so if we take this container and then we squash it down, we're having the same number of particles in a smaller space, so therefore the pressure has been increased. We're getting more collisions with the container. So what will happen is that if we've increased the pressure, then it will shift in order to try and decrease the pressure. So that decreasing the number of particles of gas, or that will decrease the volume. So if we've increased the pressure, it will favor the side with fewer gas particles because that will bring that pressure down. It will decrease the number of collisions with the container. If we did the opposite, if we decreased the pressure, it would shift to try and increase the pressure by producing more gas particles. Okay, so because if we produce more particles, we increase the pressure again. If we favor the side with fewer particles, it decreases the pressure. So to partially counteract it. Okay, so now we're going to think about the effect that a catalyst will have on an equilibrium, because a catalyst it has a particular effect. So what we've got here is just an illustration of how a catalyst helps in the Haber process, about how it allows the bonds to break within the molecules for us to form new molecules. Okay, so what we see is that when we add a catalyst, it does 3 main things. Firstly, we reach equilibrium more quickly, so it's a faster thing for us to reach that equilibrium point. That is, the rate of reaction, the rate of production is increased. Okay, so we reach equilibrium faster because the rate has increased. But we don't get a change in yield, or that is to say, we don't. It doesn't change the equilibrium position. We don't get more of any particular substance in that when we establish equilibrium because we used a catalyst. We only get there faster. Now, in the context, that may still be very important. We'll see in the Haber process that producing it faster is a good thing, but it doesn't mean that you necessarily get more overall if you let it reach equilibrium. Okay, so now just on this slide, just a bit of a summary of the different things that will happen in the according to Le Chatelier's principle. So I would strongly suggest that you pause the video now and you copy this table down, because being able to understand these changes and what it will do is really important to understand the next few things. All right, thanks very much for watching. Bye for now.